last time we introduced this concept of the CDF, okay? And I do want to make one minor correction, which is not really critical. But I think that I defined the CDF as the cumulative density function. And I realized later that probably the way that you see it actually defined is the cumulative distribution function, which in my mind doesn't make a big difference. But I thought that I would just be clear in case you're doing reading and you're trying to figure out, is this the same thing? Yes, it's the same thing. Distribution and density basically are the same concept in probability, right? So yes, but either way we called it the CDF. And that was basically the probability that a random variable was less than or equal to some value, okay? And we first started talking about that in the context of our old friends, the discrete random variables, and then we started to introduce these new continuous random variables, which mean that the random variable can take on any value, not just one of a fixed set that I can count on my fingers, right? And so kind of where we ended up last time is that I had the PMF, which, for example, maybe looks like a few discrete values, and then we introduced this idea of the CDF, which was basically kind of this idea of accumulation of probability. And at the end of, at the end of the interval, so if this is my basically PMF, the probability that I get a certain value, and this is the CDF, which is the probability that x is less than or equal to x. Well, at the end, or kind of towards the middle of the last class, I introduced a CDF for what we call the uniform continuous random variable, right? So suppose I have, something between A and B. This is like saying that nothing is happening until I get to A. Then I accumulate a constant rate of probability up until I hit B, and then I'm done, right? So this is what we called the CDF for a uniform random variable. And so now the natural question is, okay, so then what goes here, right? What is the analog to the PMF, but in the continuous world, okay? That's what we're going to talk about today. And so that thing is called the PDF, okay? So kind of, we're replacing the M, which stands for mass, with a D that stands for density, okay? So basically the analog to the PMF for continuous random variables is called the PDF, or probability density function. And so this is a really compact and important way of describing a random variable, right? If I tell you the PDF, it tells you everything you have to know about the random variable, okay? And the intuition is similar to the PMF in the sense that, the PMF kind of told us, okay, where could the values possibly be, right? Now, in the continuous time world, we mentioned last time that generally it's not possible to get any specific value, or at least the probability of getting any single value is 0 because, if I kind of take the limit as I squeeze down that interval, the probability of like being within 1 nanosecond of 80 minutes, gets smaller and smaller and smaller until it vanishes, right? But the PDF does give us some sense of where is the probability concentrated, right? So the x-axis is possible values, and then the y-axis is going to be kind of like this lump of probability, and we're going to see where is that lump located, okay? Okay, so let's be a little bit more mathematical, right? So last time we said that for discrete random variables, well, actually, I can just jump right to this. So if the CDF is given as this, and again, I'm going to make notes here. This is big F, big X, and this big X is basically the name of the random variable. And then this little x is basically a possible outcome of the random variable. Right? That's what we talked about last time. What is the definition of the PDF? Then the PDF is defined as the differentiation or the derivative of the CDF. And we're going to denote that by a little f. So again, now we got little f, big X, little x. And that's equal to, basically, I take the derivative of the CDF with respect to x. And hopefully that makes sense, right? Because how did I define, or how did I get to the CDF last time anyway? Well, I mean, to get to the CDF from the PMF, I basically integrated, right? I said, okay, how much probability have I accumulated up to a certain point? And that integral, as a function of x, is what I kind of defined as the CDF. So we integrated the PMF to get the CDF, so it kind of makes sense that we could differentiate this to get back to something over here, and that's what the PDF is, okay? And so, for example, let me just kind of like follow that conclusion, right? So what would happen if I were to actually take the derivative of this CDF? What would the PMF for the uniform random variable look like? So let's do that as an example. So the PDF for the continuous uniform random variable, here's a CDF, right? The CDF, I'm going to just redraw it here, was something that accumulated constantly until I got up to B, until I had all of the probability. So let's think about what the PDF has to look like. Well, certainly it's flat before I get to A, it's 0, right? And then after B, I'm taking the derivative of 1, right? So that's also going to be 0 over here. And then what's it going to be in the middle? Well, I have to look at the slope of this line, right? And so the slope here goes from, it goes up by 1 unit over the course of B minus A interval on the x-axis, right? So the slope of this has to be 1 over B minus A. And that means that this is what the PDF looks like, 1 over B minus A. Now, technically, I'm being a little bit hand-wavy about what happens exactly at A and B. Like I said, since no probability is actually happening at A and B, you know, technically, maybe I should be drawing these open circles and closed circles on this graph, but I think it's just much easier to draw it like a pulse, right? Don't worry too much about these vertical lines on the edges, right? Just makes sense that, you know, this is the distribution of probability across that interval, okay? And so, the PDF is the key tool now that we're going to use for evaluating probabilities, okay? So kind of on the last homework, you were using the CDF to actually evaluate probabilities. Mostly going forward, we're going to be using the PDF, right? Because oftentimes you're just given the PDF of a random variable, and then you want to do some operations that involve it, right? So how would we use the PDF to compute probabilities, right? Well, it's quite easy. I would say, for example, the probability that my random variable is in the range A to B is just integrating the PDF from A to B dx, right? So it's basically the area under the curve in that interval. And I guess maybe I should be a little bit more, I guess maybe confusing because A and B here, A and B here. Let me be a little more specific. So for example, in my uniform case, that's like saying the probability that my x value, so let's say, suppose I have a uniform random variable on the interval from 1 to 5, okay? So the PDF looks like something like this. And this has a height a quarter. And so if I want to know what's the probability that x is between 2 and 3, for example, I'm basically going to be integrating this part of the PDF, right? It's going to be the integral from 2 to 3 of my PDF value, which is 1/4 dx. So I'm going to get 1/4 x. And this turns out to be 3/4 minus 2/4 is 1/4. And, you know, in this sense, it's actually, I mean, I could have done this almost by eyeballing it, right? Because I can see that, you know, that region of the curve, under the curve, basically makes up a quarter of the total area, right? So I know that when I integrate the PDF across the whole x-axis, I have to get 1, right? Because I've got the whole mass of probability in there. And so here, I can see this is just basically a quarter's worth of the probability, okay? And really, this is not any different than what I told you last time, right? Because actually, by one of the first things that you learn in calculus, right, this is just basically what we called, if you can remember back in those days, the fundamental theorem of calculus is this. It's basically saying if I integrate some function from a to b, well, that's the same thing as basically integrating that function up to b and subtracting integrating that function up to a. And that's exactly what we defined as the CDF, right? This is like basically saying the antiderivative or the integral at the endpoints. So I mean, you know, what you were doing on the last homework was basically this. And now I'm telling you that going forward, instead I want us to start doing it this way, right, with these integrals of the PDF. Really what you're doing when you're doing these integrals is you're kind of computing the CDF and evaluating at 2 points and subtracting. It's just I'm not giving you the CDF directly, right? Okay. So let me pause and ask. Questions or comments about this? Okay, oh, question. So these guys are little f's, right? And these guys are capital F's. Luckily, it's a little bit easier for me to draw the difference between little f and capital F than it is capital X and little x. But it's good to ask. Question?
So why would we use these this way instead of just going back to just taking the integral once?
Right, so why would we not just use the CDF all the time, right? Part of the issue is that for reasons that will become clear as we go further in class, it's much easier. We're often operating on the PDF directly for a lot of other reasons, right? For example, when we talk about like the expected value, right? It's going to be very similar to how we define the expected value for a discrete random variable, except instead of summing up x times p of x, we're going to integrate x p of x, right? So knowing the CDF doesn't help us there, right? We still have to have the PMF to be able to, or the PDF to be able to solve that problem, right? And many, many further derivations in probability are going to start with the PDF straight out, right? So it's true that for evaluating like simple probabilities and intervals, the CDF is the right tool, but there's a lot more that we want to do with probability than evaluate intervals, right? That's a good question. Other comments? Okay, so let me just again be really super clear, hopefully, that, you know, important is that, you know, the PMF, or the PDF, sorry, the PDF is not basically the probability of getting x. Right? We already kind of know that any given value in the interval has probability 0, right? In fact, you know, this PDF may not even be a value in 0, 1. For example, suppose I have a uniform distribution on values between 0 and a half. So what does the PDF for that look like? Well, between 0 and a half, I have 1 over b minus a, so it's 1 over a half, and so the height of this thing is 2, right? So this is perfectly fine as a PDF, but clearly the probability of getting a quarter is not equal to 2, right? That doesn't make any sense. Probabilities have to be in 0, 1, right? So definitely don't make the mistake of just reading off probabilities off the PDF, right? What we're going to be doing is integrating the PDF, right? So for example, if I wanted to ask, what's the probability that I'm in, for example, like this region, which I'm just going to draw off as like half the area under the curve then is going to be basically, you know, a rectangle that is 1/4 wide times 2 high, which is a half. And so when I integrate, I get a number that makes sense, but the PDF value itself is not a probability. Okay. So let me just kind of review what some of the rules are, right? So all the rules that we've kind of inherited so far, talking about PMFs and talking about CDFs, all this stuff kind of like applies to this new concept, right? So kind of important properties. There are really only two. First of all, I have to have non-zero PDF values, right? Basically, you know, coming back to the very first principles, we can't have negative probabilities. Kind of why is that? Well, one kind of intuitive reason is that if I have the CDF, right, the CDF is always growing, right? I have to start at 0 and I have to reach 1, and I'm accumulating probability. So I can never lose probability, which means that whatever this weird shaped CDF curve is, eventually, you know, this is basically what I would say is non-decreasing. Which means that the derivative of that function, right, the slope at any given point has to be positive, right, which means I'm always growing. At worst, it could be 0. And so that means that if I take the derivative of this function, at every point in the derivative, I have to have, you know, positive derivatives everywhere. Or at least non-negative would be better to say. Everywhere. Because I can never get smaller. So my PDF is going to be some weird shape, but it can never be negative, okay? And the other key rule, which kind of is inherited from all this stuff, is that if I integrate from minus infinity to infinity, the PDF, if I integrate the whole thing, I have to get 1. Basically, this says if I, you know, accumulate all the probabilities all across the whole interval, I've got 1 unit of probability. That's the same idea we had for the PMF. In that case, since things were discrete, I had these sticks that I could add up, and I said, okay, when I add up all the sticks, I have to get 1. In this case, when I integrate this blob, I have to get 1, right? That says that there's 1 total unit of probability. So, you know, I have a probability mass of 1, right? 1 unit. Okay, so hopefully those rules make sense and they just kind of follow along with what we learned about before. Questions, comments? All right, so let me do some more concrete examples of new continuous value distributions that we can look at now that we are able to use this PDF, right? So now I'll basically be able to tell you, okay, here's a PDF, and I can ask you all sorts of stuff about that random variable, right? So just like in the discrete world, there are some kind of named PDFs that come up a lot, okay? So, let's introduce some new continuous random variables. Key one is called the exponential random variable. Okay? This one comes up a lot in electrical engineering applications, right? It definitely has, so again, just to back up a little bit, we often observe in the natural world, okay, so what kind of behavior does this natural phenomenon seem to be exhibiting, right? And so it turns out that we find that the exponential random variable is good at modeling things like, you know, how long does a device last before it breaks, okay? Or the time between arrivals of packets in a communication network. Or the time it takes to receive service in some sort of a queue, right? So if you're in a bank or if you're at the mechanic or wherever, this kind of notion of time to wait until something happens, right, is often modeled as exponential. So this is good at modeling things like device lifetimes or time until something happens in general. For example, you know, like a packet arriving at a router. All right, so now I can tell you about a new random variable just by telling you what is the PDF, okay? So here it is. So just like with other random variables, you know, the exponential is not just a single PDF, it's kind of a family that has it depends on a parameter, right? So in this case, the parameter is called lambda. So the PDF is defined by a parameter which conventionally we call lambda, okay? So here it is. This is going to be 0 when I'm less than 0, and it's going to be lambda e to the minus lambda x when x is positive, okay? So let's think about what that looks like, right? So e to the minus lambda x is something that decreases as x gets bigger and bigger. Remember, x here is positive, right? And lambda is also got to be positive, I should say that. Maybe just greater than 0, greater than 0, sorry. So basically, you know, let's just kind of sketch what this generally looks like. So generally it means that I plug in x equals 0 and I get lambda, and then I plug in x equals infinity and I get 0. So basically things are kind of like decaying like this, okay? And let's suppose that this is not drawn according to some scale. Suppose this is lambda equals 1. What happens when lambda equals 2? Well, lambda equals 2 means when I'm at x equals 0, I start higher, but I also decay faster, right? Because e to the minus 2x goes down a lot further than e to the minus x. So basically, I may have a much lower curve. In fact, I can use my array of colored pens, right? So this could be, for example, lambda equals 2, and then lambda equals 10 might look something not drawn to scale, like something that really shoots down really fast and then goes to 0. So this could be like lambda equals 10, okay? So the bigger that lambda is, the more likely that my random variable's value is going to be close to 0, right? So basically, a bigger lambda means that larger x values are less likely. And just for practice, we can compute what would the corresponding CDF of this be, right? So the corresponding CDF for the exponential, what would I get? Well, that's the probability that x is less than or equal to some value x, okay? And so that means that I draw a value on the x-axis. Maybe I should just do this bit. So I draw a value on the x-axis, and I ask you, what is this integral? Okay. Well, let's just do the integral, right? So luckily, this is kind of like nicely integrable, right? So the definition would be I integrate up to some value. Since this value now is the same here, I have to be a little bit careful to use a different variable of integration here. So I'd have the integral from here to here of lambda e to the minus lambda t dt, which would be equal to e to the, let's see, minus like this, right? Evaluated x and evaluated at minus infinity. And then I should think about this for a second, right? So actually, let's be clear that when x is, okay, so before I go on here. So if x is less than 0, then I should get that the CDF is equal to 0, right? So I have to keep in mind that this function really only applies up to this point, right? So if I were to draw my line here and ask, okay, what's the CDF for this value of x, I should get 0. And when x is greater than 0, then it's like taking the integral from 0 to x, right? Because the only time that this thing turns on is here. So I should get minus e to the minus lambda x plus e to the 0, which is 1. So I should get 1 minus e to the minus lambda x. So let me just write that down more concisely. So exponential CDF is equal to 0 when I'm less than 0, and it's equal to 1 minus e to the minus lambda x when x is greater than or equal to 0. And again, what's that look like? Well, I know that eventually I have to asymptotically hit 1, right? So this is kind of like my asymptote. Now, when lambda is relatively small, it takes me some time to reach up to 1. So basically something like this might be the CDF for a small value of lambda. But then for a big value of lambda, since e to the minus like 100x is going to be very close to 0 almost immediately, I might have something like this, right? So this is probably more like what the lambda equals, 10 curve looks like. I jump up to 1 very quickly. Okay, so let me pause and ask. Questions or comments about this? Yes? Can I draw the what now? Can I draw the little f's more curvy? I will try to make my f's more curvy. What would be like a nice curvy f, like this? That's more like an integral, though. All right. All right, I'll try. I'll give little tails here. I know that these tails are hard to see from the back, but I'll work on it. Okay. Other questions other than my penmanship? Okay, so this kind of may sound a little bit familiar from a couple of things that we talked about in the discrete world, right? So one thing we talked about in the discrete world was there was a kind of a thing that was related to time until something happens, right? And that was the geometric random variable, right? I keep on flipping the coin until I get heads, right? So in a way, there's kind of a relationship between this exponential random variable, which I said again, models the time until something happens. That's one thing. And it turns out there's also a relationship to the Poisson random variable. The Poisson random variable was the one where we said, okay, I've got, again, arrivals that are happening, and I tell you kind of the average rate that those things happen at, and then I ask you what's the probability that 3 people came to the bank in the same 10 minutes, right? So it turns out that those two variables are also kind of related to this. So let me kind of talk about that relationship a little bit, right? So one thing I'm going to look at for a moment here is that this is the CDF, right? I could also kind of conversely ask kind of like what's the probability that I'm in the tail of the distribution, right? So that's often something you want to talk about is what's the probability that this kind of unlikely thing happens, and that's what this red thing is we call that the tail of the distribution, right? And so if I kind of just look at the picture, what I can see is that what is the probability, so we often care about what we call the tail of the distribution. Which is the probability that I am actually greater than some value, which is nothing but 1 minus the CDF, right? So for exponential, I can see that, you know, the probability that I'm less than, or that I'm greater than some value, that I'm in the tail, is 1 minus this thing. So it's basically e to the minus lambda x when x is greater than 0. So this is like saying, okay, well, you know, if x is some really big number, then, and lambda is some really big number, that's a very unlikely thing to happen, right? So here's where the connection is. So here's the connection to the Poisson random variable. So here I'm going to just kind of shift over by one page here. Zip. So here's a setup that I might have given you for a Poisson problem, which is that, you know, let n, which is an integer, be the number of events in a t-second, you know, interval. Where this Poisson parameter alpha is lambda t. So basically, lambda is like the average arrival rate in kind of events per second. Right, so if I would ask you, okay, what's the probability that n equals 0, for example? Well, you would say, okay, how many events, so n equals 0 in a t-second interval. Okay, well, I would say, okay, how many events did I expect to happen in that t-second interval? Well, it would be lambda events per second times t-seconds. So it would be alpha to the 0 over 0 factorial e to the minus alpha, right? That was our definition from Poisson. And if I plug in this thing, I get e to the minus lambda t, okay? And I can see that this is actually here, this probability for the exponential random variable. So here, n is Poisson, x is exponential. So what am I getting at here? So there's two random variables at play. One is n, which is a discrete random variable, which is basically the number of events in an interval. And x is a continuous random variable, which is basically the inter-arrival time between events. And the upshot is that if x is an exponential random variable, if those inter-arrival events are modeled by an exponential, then n is a Poisson random variable. So that's kind of, neat, I guess. So put it this way, it makes solving some of these problems a lot easier when it comes to saying, okay, a lot of times I have a random variable that's described in a continuous way, right? So for example, I say, okay, I watch people coming to the bank, and I could either, count the number of people that arrive in every 10-minute interval, or I could just count the length of time it is between given customers, right? Those are kind of two different ways of describing the same process, right? And so let me just be clear about what the conclusion is. So basically, if the inter-arrival times are exponentially distributed with parameter lambda, then the probability that I get some number of arrivals in a certain amount of time is just like what I would have gotten had I used a Poisson random variable in the first place. I guess I should write this like this. So n is the number of arrivals in an interval of length t. Which would be Poisson in this case. Now, proving why this is true for different values of k is a little bit of a pain. So I'm just going to leave it here and tell you that we kind of showed it was true for n equals 0. Showing it's true for n equals 12 would be a little bit more complicated, so I don't want to go into that right now. But this is kind of the idea is that, there is a continuous process and a discrete process that are kind of both at play, right? And so it only works for exponential and Poisson, but that turns out to be the way a lot of these queuing and networking type problems actually work in real life. If you actually watch packets arriving at your router, they do seem like they have an exponential distribution between arrivals, and consequently it seems like they have a Poisson distribution in terms of how much you expect in a certain amount of time. So a good part of the real world of understanding why do I apply probability in real life is that you have some sort of real world phenomenon and you look at what this PDF looks like kind of from a practical point of view, and you think about, okay, well, what is a good fit between this real-world phenomenon and one of the things that I know about as named PDFs, and maybe it's not any of those, but hopefully it's a pretty good fit to one of them, right? And so just kind of like flashing forward, a key one that we're going to talk about in a lot of detail next time is the Gaussian random variable, right? So I think that by now in your EE career, you must have come across this concept of white noise, Gaussian noise, right? Stuff like that. So the Gaussian distribution is important enough that it merits a whole lecture by itself, which is going to be what we're going to talk about next time, okay? Okay, so let me stop and ask questions or comments. So on the homework, for example, there is some questions about, okay, I've got an exponential random variable. What is the probability that it fits between this interval, right? Or that the probability of x being in some certain range, right? So for that, you'd actually have to do some integration. But I may also ask you, okay, so now I've got these interarrival times. What's the probability I got exactly 3 arrivals in a certain range? Then you remember there's a connection between exponential and Poisson, and you solve it that way. Okay. Okay. The other thing I want to kind of harken back to, which is something I didn't feel like really got too solidified when I talked about the geometric random variable, is this idea of, does the process care about what has happened up to this point, right? So another kind of key concept for exponential in particular is this memoryless property. So there's also a connection for the exponential by itself that doesn't work for anything else to this memoryless property, which is kind of a statement about conditional probability. We're going to come back to that again also next time and next week. So, for example, I may ask, so suppose that x is an exponential random variable with parameter lambda. And now I want to ask, what's the probability that x is greater than, say, t plus delta t, given that I know x is greater than t, right? So this is kind of like saying, you know, and you know, making sense, this is all like, you know, positive values. So it's kind of like saying, okay, you know, suppose the buses arrive and the interarrival times are exponential, and I've been waiting 15 minutes for the bus. What's the probability that I have to wait another 10 minutes, right? So here t is 15 and delta t is 10, right? So let's just work it out, right? So this is a conditional probability problem. This is like saying the probability that both of these things happen, kind of normalized by the probability that this thing happened. And I know already this is basically like, since the top is actually just this, this is just how much is going on in the tail of the distribution. Here what I have is, this is like e to the minus lambda t plus delta t. This is like e to the minus lambda t. And so these e to the minus lambda t's are going to cancel out, and I'm going to get e to the minus lambda delta t, which is the same thing as the probability that x was greater than delta t by itself. So the verbal statement of this result is saying that if everything is exponential, it's like saying, well, you know, the probability that I have to wait 10 more minutes for the bus, given that I waited 15 more minutes, is the probability that I had to wait 10 more minutes in the first place, right? It's like the bus doesn't remember how long you've been waiting. It just, you know, has the same probability. So let me just kind of write that down. So the statement here is that, you know, probability of having to wait delta t more minutes is equal to the probability for waiting delta t minutes in the first place. That is the exponential random variable doesn't kind of remember that you've been waiting. Now that's only true for exponentials. Just like in the, just like in the discrete world, this was only true for geometrics, okay? So again, this is not a huge deal, but it's just kind of like a nice property to know, okay? And that's why we spent some time talking about this particular random variable in some detail, because it's got these connections to Poisson, connections to memoryless, and it models real-world phenomenon. So that's why I spent 20 minutes talking about it, right? It does happen a lot in electrical engineering. Okay, but there are lots and lots of other random variables, and I'll talk about a couple of them in just a second. So let me just pause and ask questions or comments. So if you must know three continuous random variables. So let me just make sure that we're all on the same page here. So key continuous random variables, right? So we have uniform, where the PDF looks like this. We have exponential, where the PDF looks like this. And we have Gaussian, where the PDF is this kind of familiar bell curve shape. And we're going to talk about this like all next time. These three things together model a lot of phenomena that you're going to come across as electrical engineers or any kind of engineers, okay? Now there are some other stranger, or at least harder to talk about random variables, right? So I think that you can expect that if I'm going to ask you problems on exam, 9 times out of 10, it's going to be one of these three things, and the other 10th time, it's going to be some PDF that I give you that you have to reason about, right? So anything that integrates to one is fair game, right? So I could have some sort of I could have all sorts of goofy shapes, right? As long as things integrate to one. Now, let me just tell you about a couple other ones that you may come across with the understanding that we're not going to really talk about these in much detail beyond right now, right? So other continuous random variables. So there's one called the gamma distribution. So the gamma distribution has two parameters, alpha and lambda, both positive numbers. And it has a PDF that is complicated. This thing is an uppercase gamma. So here, the definition of this gamma is some integral that's difficult to evaluate directly. I'm only putting this down for kind of completeness, so don't freak out about this. So the idea is that, by changing alpha and lambda, I can generate a whole family of different distributions. And in fact, I can kind of see that if alpha is equal to 1, then this whole thing just kind of reduces to the exponential distribution. So in a way, this is kind of like a more general distribution that I could use to both make exponentials and other things, right? If alpha equals, some other number, I could use this to make some shapes that I can't necessarily get with one of these three things. So I could, for example, get something that kind of looks like, something that has kind of like a nice blob for low numbers and that tails off for high numbers, but it's not centered in the middle like a Gaussian is, okay? So something where there's kind of mass that is all shifted to one side, okay? And by tuning these numbers, I could get, different shapes of distributions, which can be handy. Another one that you may come across in your travels is what's called the beta distribution. So the beta distribution, I defined this weird integral, and I can use it again over here. This is a curly f. F with a tail. So here I've got this gamma of some values. Here this kind of depends on two numbers, a and b. And here, this is only defined in the range between 0 and 1. The result of this is, in terms of shape of the distribution I can make, is that between 0 and 1, I could get something that looks kind of like this, which is nice. So something that basically is kind of symmetric, big at both ends, right? So, basically I have high probability at the ends and low probability in the middle. And this is good for, you can imagine that you've got some sort of random variable that is almost always 0 or 1, but could be with some low probability somewhere in between, right? So as an application of this, for example, in my other course on visual effects, there's a big visual effects problem called matting, which basically means that you have to assign every pixel in an image to have a transparency, which if you're a computer graphics person is like an alpha channel, right? So basically in that world, foreground is 1, background, so foreground is 1 meaning it's opaque, background is 0 meaning that you're not foreground at all, but all the pixels that are around your body, like the fuzziness of your sweater or of your skin, have these fractional alpha values, which means that you see a little bit of transparency through the edges of things, right? So most pixels are either 0 or 1, some pixels have a fractional alpha value, and it turns out that the beta distribution is not a bad idea of approximating that as a possibility, right? So that's something that I've actually really used. Let me just say, e.g., alpha values or transparencies in matting for VFX. If you really care about this, you can look at my other YouTube lecture on matting. Question? That's the PDF, yeah. And again, showing that these things integrate to 1 and so on is a huge mathematical thing. I mean, working with this gamma function in the first place is just a huge pain. So I'm not going to give you any assignments that have to do with the gamma distribution or the beta distribution, and you're not going to see on the exam, but I just want to give you some sense that there are all sorts of other PDFs out there. And just like, I don't have the book with me today, but just like there's a table for discrete random variables with their properties, there's also a table in the book for common continuous random variables and their properties, right? And so if you look at the continuous random variable table, you're going to see a lot of stuff that looks really complicated, and these are two of those examples, right? But I think in general, a PDF can be anything, right? And so another kind of common homework or exam type question, I don't remember whether there's one like this on the current homework, is, suppose, since I have a moment, let me just try to make up an exam, or a question right here. So this is not going to be a very well-formed thing. So let's suppose I've got a piece of a parabola, okay? And let me make this a little bit easier by saying that this is between 0 and, say, -1 to 1. Now, I'm making this up on the fly, so you have to appreciate that I'm just going to be winging it. So let's suppose that I know that this PDF has to look like basically b minus ax squared for x in -1 to 1. Maybe you shouldn't be taking notes on this because I'm just kind of like making it up as I go. So I guess I can fix this by saying that when x is at 1, right? So it's like saying that I know that f of 1 and f of -1 have to be equal to 0. So that means that b minus a has to be equal to 0. So I guess that means that my PDF has to look like a times 1 minus x squared, right? And now a typical probability homework exam question is, what is a? So this is a valid PDF, right? And so I have to know that when I integrate this thing, I have to integrate to 1. Otherwise, I don't have a single unit of mass. So that leads me to do something like this, where I say, okay, the integral of the PDF. And you'll notice actually that I've been a little bit lax in, I may stop kind of putting the little sub x's down all the time, partially because of the confusion that we had from last lecture is there's a big X and a small x. When there's only one random variable going on, then I can sometimes just kind of leave off that little subscript because we all know what we're talking about, right? It is useful if I have multiple random variables and I'm trying to distinguish which one is which. Okay, so I have to have this equal to 1. That would mean that I have my integral, which is a 1 minus x squared dx has to equal to 1. And now I have to do my integration. Well, actually, these limits have to become minus 1 to 1, right? Because that's the only place where it's defined. So what is my integral? I got ax minus a over 3 x cubed, x equals 1, x equals minus 1 equals 1. And that means I have a minus a cubed minus negative a minus negative a over 3. So basically, I'm just going to have 2/3 a over here and another 2/3 a over there. So I can get 4/3 a equals 1. A equals 3/4. I sure hope that's right. Let me just double check that for sanity, right? So this is like saying that my PDF is 3/4 1 minus x squared between minus 1 and 1. Does that work? Let me just do the integral again. So I get 3/4 minus 1/4 x cubed, and that's between minus 1 and 1. So I get 3/4 minus 1/4. Did I do this wrong? Silence descends on the class. No, this is okay, because then I have, there's a 3/4 x, right? All right. So I feel good about this because I get 1/2 plus 1/2 is 1. Okay, so that's definitely the kind of thing that you're going to see here and there in back exams and homeworks and so on is, what does this parameter have to be to make it work, right? So this is a good signal that you might want to brush up a little bit on being able to do simple integrals on exams, right? Let's do an example involving the exponential distribution. So suppose I've got, exponential random variable with lambda equals 2. And I want to know what's the probability that x is between 3 and 4. Okay? So my PDF is going to be 2e to the minus 2x dx for x greater than 0 and 0 otherwise. So that means that my integral is going to be from 3 to 4 of this thing, dx, which is going to be minus e to the minus 2x from x equals 4 to x equals 3. And I'm going to get minus e to the minus 8 plus e to the minus 6. Which then, if I had a calculator, I could resolve into a decimal. Questions or comments? So definitely, I don't remember exactly what I put in the current homework, but basically, you're going to have some things where I'm going to give you a name of something, exponential random variable, and you're going to have some things where I give you some sort of a shape and I ask you, okay, let's reason about what the PDF of this thing could be, right? Now that so the follow-on problem for this would be, okay, now that I've got the value of A, find me the probability that I'm between, say -0.5 and 1/2, which would require you to do this integral inside that area, right? So you got to brush up on your integration. Now, I know that there are things like Wolfram Alpha out there, which I don't deny are super useful, but you're not going to have that on the exam, right? So it's good to at least do it by hand a little bit, because you're not going to have access to numerical integration on the exams. You're just going to have to do it by yourself. I'm going to do my best to not give you anything that is crazy complicated involving integration by parts and stuff like that. There may be a little bit of that in a future homework, because I know you have a little bit of time to work on it, but I'm not trying to show that you guys are integration experts. I'm trying to show that you guys are probability experts. So the point is not to bury you in integrals.